Hi everyone and welcome to TJC Physics. Today I wanted to talk a bit about physics models and how we simplify them to be able to solve problems. Specifically, I'd like to discuss this using the model of somebody dropping a bowling ball onto the earth. Now this is a simple problem that is done quite often in like introductory physics problems, and you use Fg equals mg. But a lot of students come and ask me and say things like, well, they've heard of Newton's laws, but then they've heard that Einstein's theory of relativity supersedes those laws and all of that stuff, and it can be really confusing. So I thought it'd be instructive to maybe do a video where you see how you take some of the biggest and most complicated theories we use in physics and are able to kind of boil them down into some of the simple models that you see in introductory physics courses. So to start, here's you holding a bowling ball. Now you're going to release it and let it fall to the earth. The main bodies in play here are you, the earth, and the bowling ball. And once you release the bowling ball, the only force acting on it is the force of gravity due to the earth. We'll see why that happens in a minute. In order to answer our question, we're going to need to know what type of forces are acting on the bowling ball. There's a gravitational force acting between the earth and the bowling ball. There's gravitational attraction between you and the bowling ball. There's gravitational attraction between the bowling ball and the sun. In fact, the bowling ball is attracted to other planets, other galaxies, asteroids. Any other mass in the universe has a gravitational attraction with the bowling ball. Now, our current understanding of gravity comes to us from Albert Einstein, who came up with the general theory of relativity. Now, Einstein came up with his theory of general relativity to help try and explain what gravity actually was, and also to try and figure out why Newton's law of gravitation couldn't explain certain phenomena. Einstein's equations for general relativity can be extremely difficult to solve and requires higher level mathematics. However, it turns out for small masses, and yes, we'll consider the Earth to have a small mass compared to that of things like black holes or the sun, then it turns out that the answers given by general relativity match those given by Newton's law of gravity to a very high precision. In fact, the precision was so high that NASA only needed to use Newton's equations in order to send the astronauts to the moon. So if it's good enough for NASA, I think it'll be good enough for us to use for our bowling ball question. Newton's law of gravity says that the force of gravity between two masses, m1 and m2, also depends on the distance between them squared. As well, we include a gravitational constant, capital G. So applying this to our problem, first off, let's look at the gravitational attraction between the bowling ball and yourself. For all intents and purposes, this works out to be a force of almost zero. At least it goes to about the 7th decimal place. That's how small it is between you and the bowling ball. So we're going to count it pretty much as zero because compared to some of the other gravitational forces, this is minor. In terms of attraction to other planets, well, at this point, distances are so large that once again, for all intents and purposes, the gravitational attraction is extremely small and we can neglect it. As for the sun and for distant galaxies, well, the distances once again are so vast that we can neglect the gravitational attraction. And that leaves us with the Earth, which we can't neglect. Now, based on Newton's theory of gravity, you can see we'll measure the distance between the two objects as the distance from the center of the Earth to the center of the bowling ball. Now, this distance is quite huge due to the fact that the Earth has a large radius, about 6,378.1 meters. The reason I bring this up is because of the fact the radius of the Earth is so large. Having a bowling ball moving just a couple of meters above the surface of the Earth isn't going to result in a huge change in the force of gravity. In fact, we'll treat the radius of the Earth as a constant, and that'll allow us to treat the force of gravity on the bowling ball as a constant. Mathematically, what this will mean, if we take Newton's law of gravitation, we make one of the masses the Earth, one of the masses is the bowling ball, then part of it, you can see as I'm writing on the screen, that the G, the mass of the Earth, and the radius of the Earth are all going to be held constant. That means we just have to figure that out once and multiply the mass of the ball to get the force of gravity on. When everything in the brackets is calculated, you get 9.81 meters per second squared, which we refer to as the acceleration due to gravity. It's about the average at around sea level. We even give it a special little symbol there. We call it G, which is probably something you've learned in physics class. Now, of course, G really isn't constant. It's different on the top of Mount Everest than it is on the surface of the Earth, and it is on the bottom of the Marianas Trench. But it's a good approximation for us. And that is why we can use Fg equals mg for our simple physics problem. Well, thank you for watching, and I hope you have a great day, and I hope you check out some of my other videos.